And there are two different research questions, research question 1 and research questions 2, and that too currency hedging setting actually. So what is the kind of threshold through which we can have a kind of proper investment and with less risk factors. Basically, in financial market, we have a different kind of risk factors. So far as investment is concerned, financial investment is concerned. So out of several risks, that means maybe operational risks, economic risks, political risks, and financial risks. So this is well connected to financial risks. So we will see, what is the best way to manage so that the financial risk can be minimized or financial risk can be quantified properly. So the first question leads to, does the estimation risk fragility documented for optimized portfolio weights extend from variance to expected shortfall and from asset allocation to hedge ratio constructions, right? So basically, like again in statistics, we like to find out the error and the kind of mean and then the actual. So the difference which you have a kind of variance, error variance. In that context, we have to calculate or estimate this particular process. So question 2 is, if it does, can remedies already validated for variance minimizing hedge ratio, general portfolio weights, and shrinkage robust optimization rescue the expected shortfall objectives? So there are three different scenarios here. So I mean, basically three contributions. So extends estimation risk theory to hedge ratio. So that means the particular topic is not something new. So, but we are little bit, it's a kind of old wine in a new bottle. We are just rephrasing in a different platforms. So that means there are mean theory, variance theory, but we are trying to bring into together. So in the first case, raw ES minimization falls lost where tail dependency is the weakest. That's an estimations, noise signatures, not a risk measure flow. This is one kind of approach. Second, identifies a working remedy where convex shrinkage towards the minimum variance hedge ratio and recovery is about 91 to 107% cost effectiveness. And the third scenario is that distinguishes regularization types, turnover penalizations and lost case robustness do not deliver comparable gains, enriching this penalizing or widening the uncertainty. So so far as you can say literature is concerned, we have lots of literature, and in this particular slide we have just put some kind of selected literatures. And the first literature connected to Kim and Park. So means every particular paper. So the objective is a little bit converge, not exactly same. And accordingly, you can see from here or observe from here. And the first theory is something called as variance minimizing hedge ratio. And if you ask, because the whole objective of this paper is shrinkage, that's kind of surplus certain variations. And then in the first paper is concerns where the objective is variance minimizing hedge ratio, where shrinkage involvement is ES. And then second theory is Molar et al. So where risk measures choice for hedge ratios and shrinkage structure is not there. But the approach is altogether towards that particular financial investment and to understand the financial risk factors. And third one is actually Goldfarb and Iyengar. So it is basically general portfolio weights. Okay, so by the way, when you go for portfolio kind of compositions, where the idea is a multivariate framework and where your asset numbers are more than 2. And of course, if the asset numbers are 2 means if it is more than 2, basically like 5, 6, 7, 8, 9, something like that, then the composition will be not too high again. And for that, when you probe for 5 or 10 such combo, so weight is actually highly required. Of course, there are theories, statistical theory like PCA, through which you can derive the weight to bring the kind of composition. And in this particular theory, again, it's basically part of robust optimizations where the shrinkage and robust remedies are also there. And then this paper basically compared to means our paper is connected to this very much connected to these three papers, where the hedge ratio is well connected or well identified, where the robustness optimization or shrinkage is coming to the pictures. So in our papers, the basic idea is expected shortfall minimizing hedge ratio, and the shrinkage factor is theirs, and means we are trying to link all these three together. That's why I'm saying already informed that this particular work is not something very new. So having different kind of approach, we are bringing together, and with the latest data and the latest, different kind of currency structures, we are trying to bring this portfolio issues and trying to observe the financial risk factors. So the idea is that no prior studies test whether the shrinkage or robustness remedies and validated elsewhere extend to a tail risk hedging objectives. That's the kind of our contributions. So technically, I told you so that in the finance portfolio kind of concepts, we have to select more number of such items to justify or to involve the risk factor. So here in this case, we have used 5 different currency vectors because this particular study is connected to currency market, and European euro, Japanese currency JPA, then UK currency JBP, then Australian dollars, Canadian dollar, and US dollars. So against two return series, that country region-wise equity ETF plus CME futures, and that's what kind of hedge instruments through which we can observe this particular case. And the data time is actually 1 year, 2005 to 2026, and that to daily data, 1000 daily rolling window data. And we have derived it from the site called as Yahoo Finance. So on the basis of that, we have actually derived this particular structures. Okay, so method wise, that was the basic structure about the data, the kind of currency, and the kind of time frame which you have used for this particular work and framework. And in this particular slide, we typically try to highlight the methods which you have used. So normally this is basically time series econometrics framework, because it's one side is a financial problem, the other side is financial econometrics. So we are trying to bring financial econometrics to this financial problem, that to financial risk measurement. So in financial econometrics, so one of the standard models, something called as Arch and Gach models, and now this is this Arch and Gach cluster is actually a big concept. So altogether varieties of or various types of Gach structure is there, and one of the Gach structure which is actually latest versions or something. Means latest version means it is a kind of dynamic concept. Other kind of Arch cluster are more or less static in nature. And this is what we call as DCC Gach model, and DC stands for dynamic conditional correlations, and Gach stands for generalized autoregressive conditional autocorrelation model. And then student T Coppola, ruling tail dependence where v equal to 6, and then we finally applied Monte Carlo ES to just to that's something simulated results which you get through this particular process. It's just like something called as forecasting approach, and then regularizing this shrink and robustness vectors. So basically, I have already mentioned the whole idea is to minimize the variance vectors, or means either to minimize the error or so that means the moment you go for minimizing error, so the variance will be required to differentiate the particular process. And the particular this side the particular framework is here too, and the other side it's expected shortfall minimizing structure, and that's basically Monte Carlo optimization process. And we have gone through 10,000 simulated draws from repeated student decoupler grid search, in fact, more flexible and fair noisier. And here there are three ways to regularize this ES edge ratio. So the first one is a convex shrinkage, second one is a turnover penalty, and third one is rust case robustness. And the typical models are highlighted here against all these three, where convex shrinkage, then turnover penalty, and rust case robustness. And obviously little bit descriptions about all these three cases, something how we have derived. And now coming to this again, the little bit more about this methodology part. So how we score every estimators. So these are the formula which we use. So the first one is related to variance reductions. Second one is related to tail risk reductions. This is the prime outcome, you can say. And the third one, something called as implementation cost. And that's what technically called as turnovers, which I have already highlighted the objective of this any kind of financial investment. And so I have already mentioned, we have taken 5 different currency, and we have already applied this particular model to 5 different combo. And for examples, if you go by this is out of sample case, where the diagram reflects the behavior of 5 different currencies, and the blue reflects the MB process, variance minimizing process, and then the yellow represents raw ES minimizing process. I told you that we have applied 2 different mechanisms to justify this case. And if you look into this particular case, so the the Japanese currency case, that is JPY, which is actually in the lower end, where the hedging vector X is almost something minus 0.005, and that's how HES for raw ES minimization JPA, the currency with the weakest tail dependence. Right? So the other side, CAD is the one exceptions where raw ES already beats MBT. That means technically, if you look into this particular 5 different scenarios with 5 different currency, so Canada is the only Canadian currency is the only kind of scenario where the yellow bar is overtaking the blue bar. In other case, blue bar is actually more or less overtaking the yellow bar. So that's why in the last statement is CAD is one exception where ROES already reached the MB theirs, and that to 0.27 versus 0.221. Okay. So another way of finding the shrinkage wins is again with respect to all these structure means simulation case. So MB, rho ES, and shrinkage zero means it's a first quartile, second quartile, third quartile, something like that. So then we have seen the trend actually how it is coming, and it has a different kind of scenario altogether. And in summary, average across all 5 currency, and this is because it's a kind of optimization process, means portfolio optimization process. That's why we have taken the average here. So Sync achieves achieves the highest average HES of estimators, and the worst fell below the raw ES benchmark, that's 0.184. Okay, so now coming to key findings here. Shrinkage help most where the raw estimate is least reliable. In one side, Japanese currency is having weakest tail dependence, that's actually 91%, followed by Australian currency, the Australian dollar, that's what AUD, and having moderate tail dependence, and then finally British pound JVP, which where the shrinkage exceeds MB benchmark. So that means the mechanism is that shrinkage anchors the noisy estimate to a closed forms, low noise benchmark MB, and the estimates penalization and the worst case robustness constraint or widen the estimate without correcting it, which is why they do not match shrinkage gains. Okay, so coming to in comparison with findings and the kind of approach. So the study I cannot say that it's a perfect kind of study. The study itself, like other papers or in other words, we have also kind of limitations. First limitation is that we have taken the time frame of 1 year. And again, second limitation, maybe we have selected 5 major currency. The results may be different if we choose different currency and different time frame. And in fact, we have used daily data, but it can be used as a quarterly data and again monthly data. And again, mechanism can be change again. So some decomposition case or some machine learning techniques can be applied. Advanced machine learning techniques can be applied to find out this particular issue again. And then coming to final conclusions, not an argument against the targeting tail risks directly, an argument for answering the estimate to a benchmark that estimation risks affect the less severely. So in that case, raw ES has first most where tail dependence is weakest. That's an estimation risk signature. And then second one is a simple convex shrinkage towards MV recovers the great majority of the loss at negligible cost. And finally, not all regularization works, answering bits analyzing or widening uncertainty. So in short, our tail risk edge gap closed by a single convex combination parameter that to 91 to 107%, which we can find out from this particular slide. So that's all about my presentation. Thank you very much.
Thank you, Professor Rudra Pradhan.
Sir.
Any questions from audience or queries? Okay, Professor, do you have any published work on this?
Sir, this is a paper actually we have submitted to Elsevier journals. It is already in a review of financial research letter. Of course, Professor Kumar every year invited me, and every year I prepare a particular paper, and that paper will turn into a publication. Some of the publication I have already shared, and thanks to you. And in fact, I acknowledge also. So
thank you.
Thank you, Professor Kumar.
Thank you.
Thank you, sir.
Presentation.
Thank you. Thank you.
Bye bye.
Please stop your session.
Yes, sir. Yes, sir. Yes, sir.
We have third speaker in our session, Professor Mahesh Kumar Panda.
Yes, sir.
Am
I audible, sir?
Yeah. He is going to present his paper on optimization-based confidence regions for inverse Gaussian distribution under doubly censored data. Professor Panda, you may start your work presentation.
Okay. Am I audible?
Yes.
Okay. Good afternoon to all of you. So I thank to the organizing committee for giving me opportunity to present my current work basically on optimization-based confidence regions for the inverse Gaussian distribution under doubly censored data. So this is a joint work with my collaborator from Central University of Odisha. So this is all about the content of the talk, motivation and backgrounds, inverse Gaussian distribution and its role in lifetime data analysis. Then I will be discussing likelihood construction on doubly censored sampling. Then the next would be pivotal quantities and confidence region, and how basically we are going to get the optimal region using the nonlinear programming problem. The next would be I'll basically illustrate the application of the theory through a simulation study and then the real data applications. Okay, so why the inverse Gaussian distribution? The inverse Gaussian distribution is a natural choice for the positively skewed lifetime data. This was introduced basically in the first basis time distribution for the Brownian meson whenever there is a positive drift. And it has a lot of application in many areas of statistics like reliability engineering, survival analysis, environmental sensor, stochastic modeling. So what is the historical development and application? Schrodinger actually first derived the first basis time distribution for the Brownian meson. Subsequently, Tweedy, he defined the term inverse Gaussian. Basically, from its there is a relationship between the inverse cumulant and the normal norm. Abraham Wald, he derived it as a limiting distribution in the SPRT. That is nothing but the Wald distribution. There are certain applications you can find, like this particular distribution has been used in the dataset emptiness of the dams, then purchase incidence modeling, duration of strikes, and tracer residence time in biological systems. Here are some theoretical foundation. It has been discussed in theory of stochastic process by Cox and Miller. It has been introduced in stochastic process by Bartlett. Again, introduction to probability theory by Moran you can find. And there is a comparison between the inverse Gaussian distribution and log normal distribution. One can see this paper, Chikara and Fox. And this inverse Gaussian is a particular case of exponential family distribution. It was discussed by Cesar. So what are the research gaps and objective? In the literature, you can find many work related to Bayesian and point estimation related to censored lifetime models. Very limited work on the joint confidence region for the inverse Gaussian distribution, and especially when you look for the geometric efficiency or minimal region with respect to the joint confidence region, that has not been explored. So what are the study objectives? Because the inverse Gaussian distribution has two parameters, mu and lambda. One is shape parameter, another is location parameters. So the idea is basically to develop balanced joint confidence region for both the parameters under a doubly censoring scheme, formulate a constraint nonlinear programming problem to obtain the minimum area region, then try to compare the balance versus optimal regions using the Monte Carlo simulation. Validate the framework for 4 real datasets. So this is the inverse Gaussian distribution. F of x mu lambda, as I said, it has two unknown parameter, mu and lambda. Square root of lambda by 2 pi x exponential minus lambda x minus mu square 2 mu square x. So x greater than 0. So this is the cumulative distribution function, where you can find that this phi function is nothing but the cumulative distribution function of the standard normal distribution. The expectation of this distribution is mu, and the variance is mu cube by lambda. So as I told you previously also, this distribution has been introduced in the literature basically for the first time, first basis time distribution of Brownian meson with positive drift. So this is just a simulated things to show that how it looked like inverse Gaussian density. Now let us come to the censoring scheme. As you see then in reliability and survival studies, often we see that complete life table samples are we cannot find in all the times, because we have a lot of we can have time constant, we can have cost constant, and then there is a possibility of unit withdrawal whenever basically in the progressive sensing we see that we need to withdraw the units whenever there is a failure. So this results actually to truncate the data before every unit fails. So there are standard censoring schemes are basically being introduced in the literature. First one is type 1 censoring, where the fixed number, the observation time is fixed, and we have random number of failures. In case of type 2 censorings, the duration is random. However, the number of failures is fixed here. Then subsequently, it is in 94, Agrawala and Balkrishnan, they introduced this scheme, progressive censoring schemes. That units we have to withdraw progressively at each failure. And this is the hybrid censoring schemes, where actually we both left and right end sensors are being considered. So our study will be based on this hybrid, or that basically the double censoring schemes. So in the literature, as I said, that Bayesian distribution has been discussed for both the symmetric and asymmetric loss functions, and the MCFC techniques have been used. However, the joint and geometrical efficient confidence regions is not being discussed. So this is the doubly censored sensing schemes. Let us consider a sample where there are n number of observations are there, and then you arrange this observation. So we get the n order statistics. So here basically you can see that the first r-1 items are censored, that basically represent the left censoring, and right censoring is basically the last s number of observations. So what you can see that basically here n-n units are censored on the right side, and r-1 units are censored in the left side. So basically what you are able to observe. Hello. So basically what you can see, you can observe is the middle observation, that is n is equal to s minus r plus 1. So our inference would be based on the likelihood, inference would be based on the middle samples, and the probability mass function censored at each tail, the f of x rth order statistics, and then 1 minus f, this right, basically the right tail one, where actually these n minus n units are censored. So for the doubly censored sample, this is the mathematical functions. You get the likelihood function. So this basically, what would be the interpretation of that? That we are focused on the density contribution from the middle observations, and then the distribution function towards the left side and right censoring, you are able to see through the likelihood function. And whenever we replace r is equal to 1 and s is equal to n, then this becomes what? The complete likelihood function for the complete samples. So now we take the usual procedure, log likelihood function, and then try to find out the maximum likelihood equations. As you know that the log is a monotonically increasing function, so log likelihood equation will give you the same solution as what you are expecting from the likelihood equations. So the problem is that when you take with respect to both the parameter, you do not get a closed form solutions. Thereby we will be going for the numerical solutions. So what we are going to do, we'll try to find out the estimate of mu and lambda through Newton-Raphson or quasi-Newton algorithm. So let us first see what happens when we go for the complete sample. If you are able to observe the complete sample, then the likelihood function will be a factorization, that the likelihood function will be proportional to this nice expression. And from the factorization theorem, you can know that the summation of xi and summation of 1 of xi is a sufficient statistics for this, jointly sufficient statistics for both the parameters mu and lambda. And then one can actually use the exponential family result and see that these statistics x bar and 1 upon summation xi or summation xi, summation 1 by summation xi is basically minimal sufficient statistics for the particular distribution. So these two are basically jointly minimal sufficient statistics for mu and lambda. Now it is to be noted that under the double censoring, this complete sufficiency is lost, and in that case we need to rely on likelihood function and the pivotal quantities from the observed sensor samples, because only we are able to observe the middle observations, So that is why now we have to go for the pivotal quantities next. So as you say that for the complete inverse Gaussian sample, uh, based on the estimate of mu, we'll try to get two independent pivots, and we see that y1 is equal to n lambda head divided by lambda. This follows a chi-square distribution with n minus 1 degrees of freedom. And the second one is n into n lambda, n into n lambda into x bar minus mu square by mu cube. This follows a chi-square distribution. And we actually proved that y1 and y2 are asymptotically independent. Now what we are interested in, basically we are going to use the both confidence region, joint confidence region for these statistics and these statistics. So that is basically probability of chi-square n minus 1 comma p1 less than y1, the upper limit, that is chi-square with n minus 1 degrees of freedom p2, and similarly for yt, we find that this would be something like the p2 minus p1, and then it is q2 minus q1, and we are assigning that, let's say that this quantity is denoted by something like yes. Now this idea is basically we are going to invert the pivotal quantities to get the threshold value or upper limit or lower limit for the confidence region for lambda. So basically, if you invert the pivotal quantities for lambda, then what happens? You get a1 is equal to n into the estimate of lambda head divided by chi-square n minus 1 p1, and a2 n lambda head chi-square n minus 1 p1. And similarly, we will try to get the pivotal quantity inversion for mu also. And then if you solve this, because this is a cubic equations, so if you solve this, then you get something called as d1 lambda and d2 lambda for the confidence region for mu. So now the next one would be, yes, so the joint confidence region for both the parameter is basically what? A1 less than lambda less than A2, and that is basically what you get from this A1 and A2. And for mu, it is d1 lambda and d2 lambda. Again, this would be depending upon the lambda quantities. So this is the joint confidence region for both the unknown parameter lambda and mu. So now the probability of this would be E. So now what is the as you can see that for fixed lambda, when you see, because you are saying that lambda would be between A1 and A2, the region is a vertical strip in mu, and it is bounded by d1 lambda and d2 lambda. So if you vary the p1, p2, p1, q2, subject to the restriction that p2 minus p1 into q2 minus q1 is E, this will generate an entire family of elite regions with the same coverage probability. So now the idea is basically for each lambda, which belongs to the open interval A1 and A2, the width of mu would be what? d2 lambda minus d1 lambda. So this we have seen, yes. So just subtract d2 lambda minus d1 lambda. So yes, so now what is the idea? The total geometric region in this problem would be what? That you take the integral with respect to n lambda. So that is d2 lambda minus d1 lambda, where a1 and a2 lie, the lambda lies between a1 and a2. Take the integral. So now the idea is here, yes. So now we will try to minimize the area, which is basically, as we see that, sorry, yes, this one, yes, a that is denoted by a1, a2, d1, d2. That integral will try to minimize with respect to the constant that this we have already considered that this probability is equal to E. So now the problem can be written like this, that minimization of this area, integral a1 to a2, d2 lambda minus d1 lambda with respect to lambda, and the coverage probability is E. So this will, in this case, what we are going to do, we are going to use the Lagrangian multiplier and then try to solve the problem. So with the Lagrangian multiplier, the first order stationary condition are that rho L of rho A of A1 is equal to 0, the partial differentiation, the second part partial differentiation, third, fourth, and fifth partial differentiation will be equal to 0. So we need to solve the problem that these partial differentiations will be equal to 0. Now the issue is that if you try to solve this problem, then you do not get the closed form solutions. So in that case also, as we already discussed, that we need to either go for the numerical technique like Newton-Raphson's or quasi-Newton algorithms to get the optimum region, and which is denoted by R star. Okay, so now we are having two regions. One is balanced region, where what we do basically for the balanced region, you try to split the probability equally between two pivots. So in this case, if you solve, the P1 and Q1 will be 1 minus root over of E by 2, and P2, Q2 will be 1 plus root over of E by 2. So it is very simple one, symmetric and closed form allocation. However, this may not be the minimum area. On the other hand, as we discussed that using the nonlinear programming problem, we'll try to get the R star, that is the optimum region, by using the nonlinear programming or Lagrangian system. Okay, so this is the simulation study design, where we have considered different sample size 10, 20, 30, 40, 50, and 100. We have considered three different situations: complete samples, then 10% double censoring, 30% double censoring. And for each application, we'll try to generate the inverse Gaussian data, apply the censoring scheme, compute the estimate of mu and lambda, try to get the balanced region as well as the optimal region. And then let us compare this. So what are the simulation steps? Generate the random sample, apply the particular censoring mechanism, as we have seen, complete or 10% double censoring or 30% double censoring. Then you compute the mu and lambda, construct the balanced region, and then R star, and then compare the geometric area. So for the 10% double censoring, you can see when you take RNS, for different values of RNS, this is the balance area 65.32, where the optimal area is 38.74. And similarly, when you change the n, these are the values. So what is the key observation? When the observation is small, you can see that optimal area is basically 38.74 in comparison to 65.32. However, when you increase the sample size, the balance area region decreases as compared to optimal region. Now 30% double censoring, again you can see that when you see when n is equal to 10 basically for different RNS, you get the optimal area less as compared to balance area. The sample size is 26, and in this case, if you see the blue one is the balance area, and the red one is the optimal area. So if you compare, it is like 126.02 to optimal area 72.67. So there is a 42.3% reduction. In case of data set 2, you can see it is 65.32, optimal area 38.74. So there is a 40.7% reduction. Precipitation data set, again, the balance area is 25.52 and the optimal area is 16.9. There is a 36.6% reduction. And then finally the data set 4. Here you can see that the balance area is 20.98 However, the optimal area is 25.23. So there is a slight increase, like 23.20.3% increases. So this is the comparative summary across all data set. In the first data set, there is a reduction, 40.42.33, 40.69, and then 36.56. However, the last data set, there is an increase in the value. So how do you find the reduction percentage? Basically, balance area minus optimal area divided. The optimal regions are generally more compact, especially for small samples, and whenever the censoring is low and moderate, we find this discussion is confirmed using both the simulation and real data studies. Conclusion is basically that we discuss both the balance and optimal confidence interval for the inverse Gaussian parameters under complete and doubly censored data. We use the area minimum
only if the tumor size is below some value, because if it is bigger than some number, then well, maybe the patient has only few days left. You can think of the life length of an electric bulb, in many different aspects of life. So it could be income reporting, it could be in survival analysis, it could be in reliability engineering, it could be, well, in astrophysics. And in fact, there are some earlier references. They may not have used the term hidden truncation, but they have utilized this concept, the ideas of latent variable modeling. It is equivalently known as. The truncation, what happens, or what is interesting, is that it is much easier said than done. Hidden truncation, how do you know that a truncation has occurred effectively? You get a sense of, okay, this might be a case of hidden truncation, but what is the truncation point? When it actually happens, that is still a big question and big challenges. So there are ample opportunities for researchers to work on this. In fact, in one of our paper in Bayesian analysis for hidden truncation models, exponential we do, we were not able to fully establish all these scenarios. So we had scenarios that having truncation has happened, whether the system correctly identifies it, whether, I mean, truncation has not happened, what is the probability of the error. So we did some sort of study, but it is, I would say, is far beyond complete. So there are some open questions and challenges as well with this hidden truncation model. So in terms of mathematical framework, well, if I say X is my primary variable, study variable, so it depends on a hidden variable Y, and lower truncation could be Y bigger than some A, upper truncation Y less than B, and two-sided truncation, or both-sided, is Y chopped off between A and B. So these A and B are to be properly estimated using the data. Now, typically, this type of model, it's a standard exercise, would give us this scenario that the hidden truncated probability model of X given Y belongs to that M. M could be either one of those three situations. It is characterized by the marginal density of X, or marginal distribution, the conditional distribution of Y given X, and by the marginal distribution or marginal distributional knowledge on the conditioning variable. So these are all important on the right hand side. So if we have less amount of information or inadequate amount of information, then the associated hidden truncation model may not be fully understood in terms of real data application. Okay. Now, again, I talked about through the income reporting scenario. So these are sort of more specific direction that we can think of. And in the paper, in the survey paper, we had some of these examples specifically So income reporting, physical characteristic of elite troops, cell phone battery, cancer survival, income inequality. I must say I haven't got a nice example on astronomical data to provide, but I'm sure there are certain examples, and maybe if you are too adventurous, you can try writing in Chat GPT that okay, tell me the hidden truncation scenario in astronomical data analysis. I haven't done that. So this is sort of what happens. So you have a hidden variable, covariable. I mean, the variable y is associated with this, and on specific scenarios, depending on the choices of A and B, the hidden truncation model would be the non-truncated version of X, which is quite clear and statistically correct. We'll talk about that. Now, specifically, I want to highlight, and that's the sort of main theme of my discussion today, the ideas of two types of truncation. So we start with a scenario where the observed data is sort of truncated with the unobserved covariable. Let me just slightly slow this. Yes, that might be it. We examine two scenarios of hidden truncation models. We call it HD type 1, and in which case we start with two independent random variables. And while in the second case, we start with a sort of bivariate distribution. And it is good to mention here that a multivariate extension to this hidden truncation scenario could be envisioned in situations like I know there is a paper by Arnold on flexible bivariate and multivariate hidden truncation models, in which he talked about hidden truncation in Pareto. So you have like you observe X when for a p-variate Y concomitant, let's say K of those out of P is truncated below some value. And in fact, one of in our joint paper, we talked about hidden truncation with Pareto components, and we were able to find it's messy, it's not very nice in presentation, but we were able to get close from expression. But the thing is, multivariate hidden truncation is not that much of easy to deal with because, as you can imagine, if there are more than one or even simply two in case of trivariate hidden truncation, the efficient estimation of the truncation points, along with the induced variable distribution parameters, it's a challenging issue. I do see some papers these days where the authors they have a 7 parameter model and they came up with a estimated standard error of those estimation under frequentist approach is within like 0.0023 or something. And I'm surprised, and again I am unable to comprehend that thing, because when I dealt with the hidden truncation parameter estimation with just 2 or 3 during my thesis, I had a hard time to efficiently even come up with a likelihood ratio test. So I don't know much about this. Even with this Bayesian concept, I mean, what prior would you choose? I'll talk about that in a little bit in terms of challenges. So let me get back to these models as I was mentioning. So for the HD type 1, so this is a sort of brainchild in Arnold and Beaver. So it starts with U1, U2 two random variables with a valid PDF and CDF. Then the conditional distribution of U1 given lambda 0 plus lambda 1 U1 bigger than U2. So that's the sort of distribution or hidden truncation paradigm would be having this. So this is the type 1 of hidden truncation, and of course lambda 0 is any number in real line, and lambda 1 is not equal to 0. Now, what we observe is that, and again, this was similarly observed in their paper, that if you let the lambda 0 goes to infinity, then then this limit, it will be just the marginal or non-truncated version of the density of u1. And when lambda 1 you set 0, then we have the conditional density of u1 given u2 less than lambda 0, which is simply the unconditional density of u1 because u1 and u2 are independent. Now, if you want to include location and scale, then it will look like this. Now, what happens that, and I have established that result, that if u1 and u2 belongs to the same family of distribution, then it is in the case of upper truncation, the resulting hidden truncation model is again a member of the same family, the parent distribution, possibly with a reparameterization. So it does not augment the parent distribution in such a case. You start with a model, and basically what you are deriving is again some sort of the same family or same member of the model with some maybe little tweak to the model parameters. But if you set conditional u1 given, if you rotate this condition or change, then you get a hidden truncation model that is different from the parent distribution that you have started with. So in that case, this is sort of augment, you are bringing something new. Okay. And then, of course, the both sides is a more general case, both-sided truncation. So these are some of the simple observations that you could have. And then for the second type of hidden truncation, well, in earlier papers or works by Arnold and his co-authors, they didn't specify by HD type 1 and type 2. So we just, for the better understanding, we just separate them and classify them into two categories. So in HD type 2, you start with a joint distribution, and with the hope that you will be able to get the conditional distribution of y given x, and of course the marginals are easily available. So that's what it is. And so M here is a Borel set, which we talked about that, and this is specifically 3 forms of hidden truncation that you can think of here. Truncation from below is known as lower truncation, where M takes in the range a to infinity. Truncation from above, minus infinity to b, where b is the upper truncation point, and two-sided truncation is like M is a set, an interval a to b. Now, so as I was saying earlier, that these type of models are characterized by the 4 different characteristics in a way. It's the underlying distribution of x, the conditional distribution of y given x, the specific values of the truncation points, and some other model parameters in addition to a and b. Now, it would be at least in all my works, and as well as the scholarly works that I have seen, I haven't had a discussion on if there is any relation or interdependence between the actual model parameters with the truncation point, or to what extent they influence the efficiency of the estimation. I think that's another opening or challenging issue, and it is open. I haven't seen any work on that, so it would be nice to have some discussion on that. I haven't considered it at this point of time, but maybe in future I'll definitely think about it. And again, in this case, if you let a goes to minus infinity and b goes to plus infinity, then it goes to the unconditional density. Okay, and of course, The shape of the conditional PDF will be more sensitive. That's what we have observed for smaller values of the lower truncation point A as compared to smaller or lower truncation values for the upper truncation point B. That's what we have observed and we have mentioned in details with some pictorial devices for some conditional, I mean, hidden truncated densities in the paper. Now, there is a lot of discussion on, oh, sorry, there is a typo, it's sigma times, uh, on normal hidden truncation models, and there is a whole lot of literature on that. Of course, normal distribution is easily, I mean, they have all these closed form expression. It is nice to see. So even multivariate hidden truncated normal models, that has also appeared in literature. So it is there. I didn't include it because we, I mean, again, I couldn't find a sort of compelling reason to come up with an real scenario with the normal components. And again, if anybody is interested, I can certainly look into, and I can definitely reach out to Arnold to see his comments. Now, i- see here, and also the reason being, there is still some issues with the skew normal distribution in terms of efficient estimation of these truncation points, in the skewness parameter in uh, Azalinis classical skew normal distribution, that skewness parameter. uh, it is very sensitive to small number of observations. It is sensitive to the fact that, if lambda zero is, you try to, or you force your system to estimate lambda zero uh, with a specific error bound, then the estimated values of lambda 1 goes sort of, it's like a free fall, it's unbounded, it gives you weird values. And to see what happens with the challenges of skew normal distribution, there is a paper by Arthur Pusey which appeared in Journal of Applied Statistics in 2000, where in which the author talks a lot about these things. So it is an important issue, and it's not completely resolved. So when I started as an adventure to have, instead of just lambda 0 plus lambda 1 z, it what happens if we have a sort of polynomial scenario like lambda 0 plus lambda 1 z plus lambda 2 z squared? Then there is no answer to it. Even we were not able to come up with a very close form scenario. So it is there. So the challenges with these hidden truncation models, alias skew normal models, in case of normal components, it is an issue. But uh, you can imagine hidden truncation happening in normal components. It could be extended skew normal distribution, families skew normal, and or selective reporting models. So there are instances where it could be, within the framework of hidden truncation, HD type 1. Now, this is as a well complete reference. We took this Arnold Strauss bivariate exponential distribution, where the marginals and conditionals are there, well defined, and we talk about this um, HD type 2 as an example. So we had this math and everything, and then the hidden truncation HD type 2 for Arnold and Strauss bivariate exponential distribution would look like this. And again, if you see here, these numerical integration is required solution. It's not completely tractable expression. Okay. So, and then the more was in terms of hidden truncation was involving Pareto components, because the Pareto distribution is an useful in income modeling. So that was, in my view, that was one of the motivating factor to people explore this latent variable modeling, at least from the economics point of view. So it is by wealth inequality, insurance losses, income distribution, and many other different types of economic studies. So we looked at a combination under the HD type 1, independent Pareto type 2, and type 4 components, but one can certainly think of under uh, HD type 2 generalized bivariate Pareto model, or even there is a, in Pareto distribution there are four types: type 1, type 2, type 3, and type 4. And there is a more general Pareto distribution which subsume all these four. So you may consider that as well. So in HD type 1 involving Pareto components, we choose U1 to be Pareto type 2 with the scale parameter, I mean, location is 0, and U2 as Pareto type 2. So which is, we have these index of inequality as well. So we have this well-defined marginals, and then typically this would be, the expressions would be simplified to this. So the PDF of W would look like this, the associated CDF would like this, and then based on equation 1, if we consider the hidden truncated distribution of U1 having U2 less than the lambda 0 plus lambda 1 U1 would be like this. So this is again, it's sort of coming from Pareto type, involving Pareto type 2 and type 4. Now you may ask that, well, why did you choose Pareto type 2 and type 4? Well, if we simply choose Pareto type 2 in both the cases, then you may verify that the resulting model would simply be again a member of Pareto 2. It's not augmenting the model. So that was one of the factors that, okay, let's see what happens with, even within the family we choose two different distributions. Okay. Now, well, there are some relationship with the skew models, as I was referring probably multiple times. So typically general hidden truncated density could be represented in that equations I of x proportional to this thing, so without the normalizing constant. And you may bring into this normal logistic Cauchy distribution, student T, Pareto. But to deal with Weibull, um, but in terms of Weibull, well, this is a wonderful model and popular for survival type analysis. Again, the resulting model, if you have whether it is HD type 1 or it is type 2, if you have sort of two-sided truncation, then it gets a little bit complicated. And again, in terms of efficient estimation, that's the point. I mean, in most of these cases you will have a nice resulting density, conditional density in that form, but it is the estimation that needs to be taken care of properly. Now, I didn't include that much of this, but the alternative skewing mechanism in specifically, that was additive component, that you have the distribution marginal of x plus delta is another parameter. Y is truncated at d. So y could be less than d, y could be bigger than d, and so on. Now, what Arnold and his co-author Gomez in their 2009 paper showed that for normal hidden truncation and additive component construction, they lead to the same thing. There is no such difference. in the sense of construction setup. But for non-normal models, it is not. I mean, they have conjectured. I haven't verified for all such models. I have checked with some of them, like Pareto and everything. But I didn't find anything to challenge those conjectures. Okay.
Professor Indranil, could you
Yes.
please wind up in 5 minutes?
Oh, yeah, sure, sure. So again, definitely, I'll wrap it up. I'm almost there. So in the frequencies inferences, well, there are these maximum likelihood, fractional moments, quantile methods, pseudo likelihood methods, but challenges is the no closed form estimators, weird type normalizing constant, and there is small sample issues. In the case of Bayesian, it is a, what choice of prior you would have for the truncation points. There is a lack of conjugate priors and model specific implementation, but to some extent you can, handles intractable normalizing constant, because in Bayesian analysis we do not necessarily need that normalizing constant. So that's another plus point to this. But there is no a general Bayesian framework. So there are some applications, opportunities, model discrimination procedures. This might be helpful. High dimensional hidden truncation involving multiple hidden truncation points. You may want to come up with some ideas on general Bayesian framework, and of course, with some machine learning application. So in summary, this is hidden truncation models addresses latent selection mechanism, and there is an rich connection with the skew normal and other skewing paradigms. It has a wide range of application from different aspect of real world, but overall statistical inference remains challenging. Okay, so and these are sort of my references, and this is I was referring to multiple times 2009 paper. We did some of these work on Pareto data and multivariate. Okay, this, and then there was I did some work on Bayesian aspect and associated issues, but to some extent. And this is the paper as a book chapter that I'm referring to. So with that, I'll stop here. Thank you for attention to this talk. Thank you. Questions?
Yeah, Professor. Any question? So, could you please clarify the data structure again? Because in the generally hidden truncation means you don't include the data which is below some point or which is above some point. So here we have a bivariate kind of data, and then
Well, that's a good question. So it is so in HD type 1 we have this clear distinction that you start with two, so you have two components that you observe Y only when X is below or above or something. uh, for HD type 2, what we were, or actually it's not me, but what the original proposal was that, well, in concomitant variables, so let's say there are two components like a person's, and again I'm going back to that military application or selection. Height and weight is in a way is related, at least to the selection criteria. So they treat height and weight as a sort of interrelated. They have some sort of dependence in terms of getting into that list. And then you will observe those height values for the applicants only when, let's say, the weight is below some value,
you know
or
some.
weight is
But
between some reasonable limits that the army or navy wants to see. So that's the kind of argument that goes with this.
yeah. Anyway, nice talk. So I also learned a lot of things. So maybe there is some Wsta disease-based estimation for truncation censoring. Maybe I will try
Oh,
to
yes.
do that.
Okay. Okay. Thank you for this. In fact, progressive censoring. And again, I'm not going to take other person's time, but
Yeah.
progressive censoring something that has to be done, and we have to find a relation to that. So, and my collaborator Tony knows more about this, and we are planning to have something on that in that direction.
Yeah. Thank you, Professor Indra,
Thank you. Thank you.
for a nice
Thank
talk.
you for it.
So we will move to next now.
Our third speaker is Dr. Indrajit Kumar
Indrajit
from
Kumar.
Central University of South Bihar, recognized for his valuable academic contributions to mathematical statistics and applied data analysis. Welcome, sir. Now I respectfully invite our session chair, Dr. Sudesh Kumar, to kindly take over the session and commence the proceedings.
Yeah. Dr. Indrajit Kumar, you can start your talk. It is, yeah. It's fine. We can't hear you. Maybe you are muted or
earlier we could see your slides properly. Now it is not. Also, we couldn't hear you. Not audible. Okay. So unmute your mic. Then Kumar, whether there is more other device rather with your laptop, switch off the audio of the other device.
Am I audible, sir? Hello?
Yeah, now it is out. Now it is clear. Audible.
Thank, thank you, sir.
Now we have to share your slides.
Yes, sure.
Okay.
Is my screen visible?
Yeah, it's fine. Excellent.
Yeah.
Then press the button.
Good evening, everyone. I'm Dr. Indrajit Kumar, Assistant Professor in the Department of Statistics, Central University of South Bihar. And today, I'm going to present my research work, a statistical inference for the inverse Pareto distribution under progressive type 2 censoring. So what is censoring? Censoring is actually censor data appears whenever the event time of interest is only partially observed. Means when we are going to conducting any experiment, like we are testing the electric bulb or we are testing the any medical patients. So that time we can observe either we can observe complete information or either we can get partial information, and partial information not always garbage, so that we can make some information based on the partial information as well. So this because data is very important, so somehow we can make inferences based on the sensor data that can be beneficial for the like cost wise or time wise. So censoring can be two types, like it can be intentional or it can be unintentional. Unintentional means it may happen accidentally or randomly it may happen. So there are two types, intentional and unintentional. When we do not have sufficient time to continue the experiment, whatever ongoing experiment going on, that time suppose we have to close the experiment within 2 hours, so that is the restriction. We are forced to stop the experiment. That time we have to do we can say that it is intentional type of censoring. And if we do not have we have to get at least minimum number of failure or minimum number of observations. That time we have to continue the experiment till getting a sufficient number of failures. So these two types of majorly two types of censoring scheme, intentional and unintentional. So in reliability study and live testing experiment, all unit fail because like all unit you may get or may not be. So this is the limitation. So that time we can conduct like for example medical follow-up, patient may not experience event before the end of a study and may enter the like biological process or whatever the challenges patient having, they might have decision to move to other hospital. They might during the treatment they might get fail their whatever the disease they are having. So that type of censoring can be possible. So this is the mechanism. Suppose we are having n number of experimental units are there. We are going to test that unit. If we are getting exactly X number, like all the if we are getting all the unit failed in the experiment, that time we can get exact observation. And if we are getting like after C, C is a time at which we after that we do not have further information after C, that time right censoring. And before before something happened, and today we know that any patient had some disease after diagnostic, so this is the left censoring. And interval censoring, it is in between, during the left and right. So this is the scenario we can get. And current status, it means we can observe either it is also called random censoring. So current situation, what will happen, like whether it is observed or it is censored. So that time it will appear like this. Okay, so this can be also explained in this schematic diagram. We can get exact failure, and we can get right censored, we can get interval censoring, and we can get current situation, whether it is random, it is censored, or it is failed. So basically, in this study, our objective is to study the progressive censoring scheme under inverse Pareto distribution. So progressive censoring scheme, it is from last more than 2 decades. This censoring scheme has got much attention in literature. It has been shown several application of progressive censoring, because this censoring scheme allow us to remove the experimental units from the experiment. Live unit, surviving unit, we can remove. Surviving unit we can remove means we can save time and money as well. How we can save time? Because if we are having thousands of experimental units are there, and some units we all know all the experimental unit, after the experiment, all the experimental unit has been destroyed. So this progressive censoring scheme can be cost effective, because of it can save some live unit as well. So this is widely used censoring scheme in reliability theory. Because of flexibility of remove the experimental unit from the experiment during the experiment. So this is very popular censoring scheme in literature. So this is the algorithm how to generate the progressive censoring scheme. Suppose we are having complete data, and from that complete data, this x1, x2, xn has taken under censoring scheme, and then this is complete data, and this is the removal. So removal pattern can be decide how we can implement that censoring scheme, removal, how we can implement. So at the time of first failure, the first R1 unit can be removed, R1 live unit can be removed, and the algorithm can be designed in this likewise. Okay, so this is the schematic diagram of progressive type 2 censoring scheme. N sample, we have a start with N sample. At the time of first failure, we can remove the R1 survive unit, and then at the time of second failure, we can remove R2 and so on. And in censoring scheme, we will get at least M number of failure, that is prefix. So that observed failure will be x1, x2, xm, and the removal will be r1, r2, rm, and such that r1, r2, r1 plus r2 plus r, this so on n minus 1, and this will be given. So in this case, whenever we are having data, we for making any statistical inferences, we need any we required any probability distribution to make some inferences. Either even in case of non-parametric cases, if we do not have exact exact probability distribution of the data, exact pattern of the data not matches with the particular distribution, then we can go for non-parametric test. In case if our data following some pattern, so that time we required some particular probability distribution to make some inferences. So in this case, like suppose x follow inverse Pareto distribution. X is like surviving x. We can say that it is failure time. So failure time of the experimental unit. So and it is following the inverse Pareto distribution. Suppose it in place of inverse Pareto, x can be follow. If suppose x not following inverse Pareto, it may follow something. So that time we have to choose that particular distribution. So here our objective is to like consider x. Suppose x following the inverse Pareto distribution pattern. So that time we have considered inverse Pareto distribution. It has one parameter, shape parameter, and this is the PDF, CDF, and survival function. This is the PDF and hazard rate plot, and from the hazard rate plot we can say that the inverse Pareto distribution has inverted like increasing, decreasing, and inverted bathtub shape pattern, and this pattern is very useful in like survival analysis. In this case, uh, a disease which is mortality peak after the some time, the disease declines slowly. So this type of data, this type of pattern can be a study with the inverse Pareto distribution. So like whenever we are having any model, so that model can be estimated through suitable estimation technique. Like in regression, we are generally using least square estimation. So here we are having the probability distribution that we are finding the likelihood of the failure rate, failure observation. So this is the likelihood function of progressively failure failure observation. So this is the PDF, and this is the survival function, and this is the remover. So this is the likelihood function, and for the inverse Pareto distribution, this can be likelihood can be written as equation 1, and their corresponding log likelihood given by this one. And to find out the maximum likelihood estimates, we have to either maximize these equation by using some calculus method. And then after in this paper, like in this work, I have used two estimation technique, one classical maximum likelihood estimation techniques, and other Bayesian estimation technique. So Bayesian estimation, like it refers to when we are having any prior information about the parameter. So that time we can use Bayesian information. If we do not have, we can use the maximum likelihood or classical information. So if we are having any prior information, then the Bayesian estimation technique can be apply, and it can be produce like updated result. It can produce updated info. It can update the information whatever the prior belief we are having. So by incorporating the maximum likelihood estimation with the prior, so this is the gamma prior we have taken for the parameter, for the model parameter, and after the incorporating the prior belief in the maximum likelihood, this is the posterior distribution. And this posterior distribution showing like it is not very close form, so we can use any iterative method, Bayesian iterative method. For the particular problem, like we have taken the MCMC technique. So MCMC technique followed by Metropolis Hastings algorithm. So in this case, we can make the inferences based on the sample based information. Like computation. We can do the sample based estimation. So how to, like, sample based means, we have to generate the m number of sample of parameter, and then we can take their modes. So this is the for the particular algorithm, this is the steps to execute the algorithm. Like in this case, we have to consider the candidate points for the from the normal distribution for drawing the sample from the posterior. And these are the, like, we have taken the initial guess, and we have to generate the candidate point from the proposal density, and this is the, like, minimum of this value we have taken, and we have generated finally m number of sequence. And then under a squared error loss function, the Bayes estimates of theta is given by this one. And we also computed the HPT credible interval for the theta by using with the help of generated sample. So for the developed methodology, in this study, we have performed an simulation study to, like, examine the performance of estimation techniques considered in the study. So this is the, like, several combination of progressive type 2 censoring plan, and this is like n we have taken like n number of samples, and this is the effective number of samples, prefixed number of progressive sample. And this is the schematic, like, this is the schemes by which like removal has been decided. So this is the several combination. Based on these combination, like ML and Bayes estimates of parameters has been computed. Like this is the average estimates and this is the MACs. For both cases, MLE and Bayesian estimation techniques. Prior zero refer to the non-informative prior, and for which we have considered the prior alpha and B, A and B is equal to 0.001. And the prior one, we have decided like ratio of the hyperparameter is equal to the true value of the parameter. So this is the average estimates of estimates under Bayesian under MCMC technique, and this is the like average length and coverage probability under HPT credible interval for both cases, prior 1 and prior 2. So this is the for parameter theta, and this for reliability function. So we have estimated the reliability by taking t is equal to mission time, we have taken 0.8, and the reliability where true value is this one, and this is the average value. So similarly, we have computed failure rate function, and from the table we observed that the MSEs of ML and Bayes estimates of the parameters and reliability characteristics decreases as n increases in almost all cases. And it is also observed that the Bayes estimates obtained under prior one consistently outperform those based on prior zero and the maximum likelihood estimates. Overall, we can say that the Bayes estimates under prior one outperform when we are having any prior information. Average length, like similar pattern of outcomes can be observed in the interval estimation. So, and the coverage probability. After doing those simulation and mathematical development, our next objective is to like how we can implement implement our considered model and like our research work in real life application. So model illustration here we consider the survival time of 44 patient with head neck cancer treated using combined radiotherapy and chemotherapy. So this data were reported by Afron in 1988. So this is the observation. It is given in day. To illustrate the proposed methodology and the complete sample was converted into the progressive type 2 censored sample using the algorithm given by Balakrishnan and Sandhu in 1995. So based this data has been transformed into progressive type 2 sensor data, and then whatever the simulation we perform, similar type of estimation method has been applied for the this data set. So before implementing that methodology, we have to check whether the consider data following inverse Pareto distribution pattern or not. So for which we have to test goodness of, we have applied the goodness of fit test like case test and AD test. We applied for that, and here the p value suggesting that this data following inverse Pareto distribution. And we also check the some competing model with the IPD, and we come this table showing the table matrix showing that the inverse Pareto distribution outperform these two models, and there is these associated result. Then after for the considered data, we applied 5 different censoring scheme. It can be censoring scheme. It means this plan is removal. We can decide in different ways. Either we can remove from a starting, either we can remove from end, we can remove in between, and we can remove one by one. Whenever when we the censoring scheme one, it shows that there is no removal, it means this is the complete data. It is showing that complete data pattern. So this is a special case of progressive type 2 censoring scheme that can be converted into complete data. And this pattern from the last from a starting, there is no removal up to 34 observation. Later on 9 observation has been removed. So that right removal, it shows the right censoring. And in case of third plan, it is showing that 14 observation removed from a starting. It removes 14 observation. It means it is the uh, like uh, left censoring. And this is the same pattern, and this is the mixed type. So it is removing after getting one failure, we remove the one unit. After getting one failure, we remove second unit, likewise. So seven removal was there from the median. So for the particular pattern, this is the observation we observe. This is the 35 observation removal. Sorry, 35 failure observation. This is the 30 failure observation with this scheme. So based on this, these
Adina?
Sir,
Yeah.
good
Now it is
evening,
like
everyone.
initiate the session. You can introduce the chair and also briefly introduce the chair
Yes, sir.
and thereby invite the chair to do the, continue the further proceedings and support him.
Good evening, everyone. Welcome to the next technical session, a plenary session as part of WSTA 2026 11th International Webinar on recent trends in statistical theory and its application. It is my pleasure to introduce our session chair, Professor S. Satish from MG University, India. Professor Satish is a distinguished statistician with over 35 years of research experience. His research interests include probability theory, stochastic process, and reliability theory, and he has made significant contribution to these fields through his research and publications. We are honored to have Professor Satish chair this plenary session. It is now my pleasure to introduce our first plenary speaker, Professor Michael Evans from the University of Toronto, Canada. Professor Evans is a leading researcher in statistical inference, mathematical statistics, and statistical computing. Our second plenary speaker is Professor Muhammad Ahsanullah from Rider University, USA, a fellow of the American Statistical Association and the Royal Statistical Society. Professor Ahsanullah has authored over 40 books and 360 research articles. We are delighted to have both our distinguished speakers with us today and look forward to their insightful presentations. I now respectfully invite Professor S. Satish to kindly chair the session and commence the proceedings. Over to you, sir.
You're muted.
Yeah, Professor Satish. Satish is here in the group. Hello, please.
Please unmute.
Please unmute your mic. Satish, please unmute your mic.
Hello.
Hello.
Okay. I'm sorry. Okay. I'm thankful to Ms. Adina for the nice introduction and also Professor Satish Kumar for inviting me to chair this session. So we have two speakers here, Professor Michael Evans from University of Toronto and Professor Hasanullah from Rider University, New Jersey. Let me cordially invite Professor Michael Evans to present his ideas here. Professor Evans, please.
Thank you. Can you see my screen? I don't think so somehow.
Not yet, sir.
Yes, well, I've said share screen. Okay. Window. Well,
Yeah, it can go. And open the slides.
my slides are open, but somehow the screen is not showing up.
Yeah. Now.
Not sure what's going on there.
Perhaps you may click show my screen.
I have share screen on.
Show my screen anyway.
Yeah, I did that, and now it just goes into an infinite loop.
I hope stop sharing and share it once again. That's fine.
Okay, try it again. Okay. It's giving me three options: Microsoft Edge tab, but that's not it. Window, no, entire screen. And the entire screen, I get this problem. So I'm not sure what the problem is. I've never had this difficulty before.
Yeah, I think you want to share it once again, Professor, so that.
Okay, I've shared it.
Yeah, but not it.
I'm just not seeing that it goes there.
Could you please use this entire screen?
Entire screen, that's what I did there.
Okay.
Entire screen, but am I, can you see my slides now or not?
It's not.
No, sir, not yet.
Okay, so.
Have you clicked on share button?
Yes.
Okay.
I have, but
it's blue, right? It's
there might be a small window.
I'm not sure it's at my end, actually, if somebody has to allow me to present somehow, but it is not.
Oh, okay. If it's difficult,
Yeah, we can
share it from here. Could you please send it to your email, to Dr. Sadish Kumar's email?
Okay.
Okay, so
please
we can
please share it.
from here.
We have a time, Professor. No problem, because second speaker has some difficulty in coming, so we have time.
Okay.
Don't worry about the time. You please send it.
Okay.
Yeah, we can share
Okay.
it. Okay, Professor.
I will send it to you. Yeah. Okay, I have sent it.
Okay, please.
That is
Yeah.
fine. We can try it again. If needed. Try it.
Send it. Okay.
Yes.
Okay.
Yes, now we can see the screen. Professor Evans, I hope you can also see, right?
Yes, I can see it, yes.
Yes, please, sir. So, Professor
Okay.
Evans will be talking on confidence, statistical evidence, and relative belief with applications to a problem in particle physics. So, please, sir, you can take some time because the second speaker is yet to report.
Okay, great.
So
Thank you
please
very
take your
much.
time. Okay.
Thank you very much. And thanks very much for the opportunity to talk. I've talked before at this conference, and hopefully you're not getting bored with my message, because it's always kind of the same message, namely that I think in statistics we have to be more careful about the notion of statistical evidence. Okay. So what's the aim? This is a foundational topic, so we go back to the very start. What's the aim of statistics? Well, I've written it out what my purpose is. The purpose of statistical analysis, I'll just read it here, in any scientific domain is to answer questions of interest in the following sense. Observed data contains evidence concerning the answers to whatever the questions were, and the goal of a statistical analysis is to reveal what the evidence indicates and how strong that indication is as clearly as possible. And my thesis, if you like, governs the way I approach statistics, my research in statistics, is that we have to be clear about how evidence is to be measured. And I don't think we really are. Now, this is a historical debate. It goes back many years. In fact, to the 1930s, where a debate between Fisher and Neyman, which I would call Fisher evidential versus Neyman's behavioristic. And that is relevant to my talk today, because I'm going to present things from the point of view of evidence, and this procedure that I'm talking about that's used in particle statistics comes directly from Neyman, his paper in 1937. And there's another aspect of this, and this may have something to do with why the evidential approach is not as perhaps as well taken up these days in statistics, is because we need to be proper Bayesians. We'll see why in a few moments. But the interesting thing about it, what I call relative belief, frequentism still plays a role. So it's not like it's Bayesian versus frequentism. Both Bayesian and frequentism have a role to play. And the way I like to say it is that the evidential approach is for inference, while the behavior approach is for design. Okay. Oh, now I'm having some trouble getting it to advance page. All right, we go. Whoops. Okay, the physics problem. So it's a very simple, well, it seems like a very simple problem in some ways, that in particle physics, people are counting, however they do it, numbers of particles, events in the Large Hadron Collider. And they're modeling that by a Poisson distribution. But it's a Poisson distribution with a bit of a wrinkle. And the mean is lambda plus b, where for the moment we'll consider b as an unknown constant. B is the number, is noise when they do this, right? And so b is representing the noise. And typically, because they've done lots of other experiments, they have a pretty good idea of what the value of b is. Now, I'll talk about that case, but I'll also talk about the case where b isn't very well known and is a nuisance parameter. But our goal here is to make inference, estimate lambda, and also make an assessment of the accuracy of the estimate. Now, why don't we use standard asymptotic likelihood-based confidence intervals? Well, the physicists don't, because they suffer from a problem. Oftentimes, they get very small counts, and when you try to apply the asymptotics, sometimes the confidence interval will contain negative values. Now, we know that lambda is greater than or equal to 0, so negative values are not possible, right? So what do you do in a context like that? Well, one thing that people would obviously think to do is to truncate the interval. But then if you think of the confidence interval, the length of the confidence interval as being a measure of the accuracy of the estimate, which will be the MLE, it doesn't represent that accuracy properly, right? Because you've truncated part of the interval. So there's lots of work on this in physics. I wouldn't say the physicists are entirely happy, but the main approach used is due to Feldman and Cousins. And that's based on Neyman's 1937 paper, and I'll call these here Feldman-Cousin confidence intervals. And their work, by the way, was when there were no nuisance parameters. And there's a number of other papers on this topic as well. It's still a topic of some consideration in high energy physics. Okay, so what is a Feldman-Cousins confidence interval? So we have ingredients. What are the ingredients? Well, they have a model, which here will be, I'm not just describing the physics context here, I'm describing the situation in general. We have a model and data, and I call that an inference space, right? So the model is comprised of a bunch of density functions. That's my p dot slash index by theta, right? And we want to construct a region, call it C sub gamma, here, right? That goes from the sample space into the set of subsets of omega, of capital theta, pardon me, such that the probability that the true value of theta is in this region is at least equal to gamma for every theta in the parameter space. Everyone is familiar with that. Now, Feldman Cousins, they use, as part of their construction technique to obtain this region C, they use the relative likelihood. And the relative likelihood is just a density function divided by the supremum of the density function, supremum over theta, right? So this is always a value between 0 and 1. And at this point, I would just remind you what a likelihood region is. A likelihood region is the set of all theta where the likelihood function at every value in C is greater than or equal to some positive constant C. Now here's the construction. So this is Neyman's construction, really. So I call it the Neyman-Feldman-Cousins construction. And it's really a counterexample to this construction that my concerns are with this construction and what it produces. So we get what's called an acceptance region. We take all the sample values for a given value of theta and a given constant c. We take all the data values that give a likelihood, a relative likelihood greater than or equal to c. And the idea is that if you observe x, the data, in this set A theta C, then you accept the hypothesis that the true value is equal to theta. So this is Neumann's accept reject framework, right? And then you're going to, or what C should I use? Well, for each theta, you determine C sub gamma of little c sub gamma of theta is the supremum over all C, so that the probability content with respect to the theta distribution of that set is greater than or equal to gamma. Okay, and then finally you construct your confidence region. It's the set of theta with given data, right? It's the set of theta so that X is in the corresponding acceptance region. And sure enough, if you just think about it for a little bit and see the coverage probability for this region, I should have had a sub gamma there, is equal to the probability that it's the data is in the acceptance region, which now of course is greater than or equal to gamma for every theta. Okay, so that is how one constructs a confidence region for theta using the Neyman and Feldman-Cousins. Feldman-Cousins, I think the unique thing there is they're using their relative likelihood, but it's basically due to Neyman. Okay, so here's an example. I'm not going to go through all the arithmetic here. It's a bit tedious, but I like simple examples. If I have a statistical procedure and I try it on a very simple example like this and it doesn't work, then I think there's a problem with the statistical procedure, okay? So I have a model here. I've got three distributions in it, P1, P of theta 1, P theta 2, theta 3. There's three of them, and the probability distribution goes horizontally for each theta, and the likelihood goes vertically, right? So when I observe the value 1, the relative likelihood is given by these values. I observe the value 2, the relative likelihood is given by these values. And I go through the construction technique, and I constructed here all possible acceptance regions that I could get in this problem. I'm not going to bother going through it, but I just implement the methodology that I just described. And by the way, this is all in the paper that I referenced at the start. And so what do I wind up with? Well, if I take gamma equals to 2/3, so I'm asking for a confidence region that has coverage probability at least 2/3, I wind up with these three values, right? When I observe the value 1, the confidence 2/3 confidence region is theta 1, theta 2. When I get 2, it's theta 1 and theta 3. And when it's 3, I get theta 2. Now, these are the actual coverage probabilities. Now, the problem is with this, however, and it is the lower bound is indeed 2/3. If I look at the value of the confidence region when I observe 1, it's not a likelihood region. And the reason for that is because, the likelihood at theta 3 when I observe 1 is greater than the likelihood at theta 2 when I observe 1, but theta 3 is not in the region. So it's definitely not a likelihood region, okay? Now that's one of the problems with the Feldman-Cousins, so we'll see why later. We want these regions to be likelihood regions. Now I did it again for gamma equal to 11/12, which is like a 92% confidence region. And something even worse happens here. I get that the confidence region is equal to the entire, for two data values, equal to the entire parameter space. Now such confidence regions are sometimes called improper, or I like the word absurd. The reason that they're absurd is that suppose I observe 1, and I report to you the confidence region is equal to the entire parameter space. Well, the confidence is 11/12, but you look at that and you say, but I know of absolute certainty that the true value is in that set. So the confidence of 11/12 seems kind of absurd, irrelevant there, right? We don't want confidence regions that equal the entire parameter space. Now, this happens not just in this example. It happens in a number of other examples. The method I'm going to talk about, which gives confidence, never suffers from that problem. And in general, there's some nice papers by Andre Plante in the Canadian Journal He really looks carefully at the whole concept of confidence region, and he's certainly a fan of confidence regions, I would say too, but he's very pessimistic about, basically if you pursue just getting coverage probability, these regions can have other unfortunate properties, like the ones I've just pointed out. Okay, so I want to talk now about measuring evidence. So when we're talking about measuring evidence, we don't really need to be statistical. We can just think in terms of probability, because that's where the characterization comes from. Okay, so I have a probability model, and I have an observation that comes from that probability distribution, but I don't see it. It's observed, it's concealed from me somehow, perhaps by the future. And I'm interested in whether or not this future value or concealed value is going to be an event A, where the probability of A is greater than 0. And that's our initial belief, right? P of A, that's our belief to start out with, that omega will be in A, little omega will be in A. But we've got some information. This is the data. We're told that omega is in a subset, an event C, where again, the probability of C is greater than 0. So our belief changes. This is basically a principle. We're not forced to replace P of A by P of A given C, but we more or less think that that's the right thing to do. I don't think that's a controversial principle in statistics. You have to be a bit careful in its implementation, but it's a generally accepted principle. Namely, we replace our initial beliefs about A being true by the conditional beliefs. Now that's where the principle of evidence comes in. And I think it's one of the most natural principles and has a long history. For that probability model, we have evidence in favor of A being true if our probability after being told C is true goes up. Our beliefs increase, then we have evidence in favor of A being true. If our beliefs decrease, we have evidence against A being true, and we don't have evidence either way if they're equal. If they're equal, that occurs. Equality occurs if and only if they're statistically independent. So observing that C is true tells us nothing about whether or not A is true. Now I think this is a put in quotes, an obvious characterization of evidence. It's been around a long time, probably 100 years, although not really terribly exploited in statistics. But in philosophy of science, they talk about this, and it's called confirmation theory. And some very well-known philosophers have published on it. Now, really what I'm doing is making this into a statistical context, which the philosophers never do, excuse me. So they wind up with paradoxes that they can't resolve, but the statistical context does. That doesn't tell us anything about the strength. So we know now, after we've seen that C is true, we know whether we have evidence in favor of A being true or evidence against. But it doesn't tell us how strong that evidence is. There's a natural way to measure that strength. Namely, we just have, okay, how strongly do we believe what the evidence says? So if we've got evidence in favor and this probability that we now believe, our probability measuring our belief that A is true, if that's big, then we have strong evidence in favor of A being true. If we have evidence against and this probability is small, then we have strong, excuse me, evidence against A being true. Now that's a very simple context. We're just considering A versus A complement. But suppose we have a partition. So I divide omega up into subsets that are mutually disjoint and their union is equal to the whole. I should have been cap theta. Oh no, omega, I'm in the probability domain here, okay? And each one of those sets has positive probability. And again, I'm told that C is known. So I can tell for each one of the elements of the partition whether I have evidence in favor of it being true or evidence against it being true. Now, in this context, I need a way to rank things, right? And the natural way to do that is based on what I call the relative belief ratio. And the relative belief ratio for an event is just the conditional probability of the event divided by the unconditional probability, or what I'll call the posterior probability in the numerator and the prior probability in the denominator. And that's a valid measure of evidence. Valid, I mean that it agrees with the principle of evidence, because there's a cutoff, namely if the relative belief ratio is bigger than 1, then I have evidence in favor of A being true. If the relative belief ratio is less than 1, I have evidence against. There are other valid measures of evidence, but this seems to be the one with the best properties. And so now I can rank them. If I have the relative belief ratio for AI is less than the relative belief ratio for AJ, and they're both bigger than 1, then I can say, well, there's more evidence for AJ than there is in favor of AJ than there is for AI. And similarly, going in the other direction if they're less than 1, right? And that leads me to a natural estimate. I want to estimate which partition element contains the true value of little omega. Well, I'll just take the value that has the most evidence in its favor. That's finding the supremum of the relative belief ratio. I call it A on C. And what about the accuracy of that estimate? Well, I'll look at this, what I call the plausible region. And the plausible region just consists of all the values, all the partition elements that have evidence in their favor. And then I can calculate the posterior probability of that set, the plausible region, which is down here. And I know if this region is small and that posterior probability is big, I know I have strong evidence, or this estimate, AI and C, is an accurate estimate of the true partition element that contains omega. Now, sometimes I might want to assess whether or not the AI, I have a particular partition element that I think contains the true value omega. And then I know right away if I calculate the relative belief ratio at AI sub 0, if it's bigger than 1, I have evidence in favor of that being the true partition element. If it's less than 1, evidence against, and no evidence either way if it's equal. And then I can measure the strength of evidence. Now here, because I've got multiple values of the partition elements, I do that via this posterior probability. I calculate what's the probability that the true partition element has relative belief ratio no greater than the hypothesized value. And if that's a big probability and I have evidence in favor, then I have strong evidence in favor of A sub I0 being the true partition element. Now that's all probability. So this notion, there's no statistics here. This is all done purely within the context of a probability model, but I can apply that immediately when I go to the Bayesian context where I have a full probability model, right? I take the prior probability on theta, which I'll denote the prior by pi, and I take the conditional probability of the data given theta, and the joint is given by their product, and that gives me a probability measure on the joint theta in X, right? The joint distribution of theta in X. And so I can go to the relative belief ratio. Now, the previous example was everything was discrete. I'm not going to go through the details here, but I can do everything in the continuous case as well, just by taking limits. And when I do, the relative belief ratio for theta is given by the ratio of the posterior probability density of theta divided by the prior probability of density of theta. And an important equality immediately follows from, we know the posterior is equal to what? Is equal to that product divided by the prior density of the data. When I stick those in, I wind up with this alternative expression for the relative belief ratio. And the nice thing about this alternative expression is you can see right away that this is proportional to the likelihood function, right? This thing on the right here. So the relative belief ratio, this is one of the nice features of the relative belief ratio, is proportional to the likelihood. Now, it's not a likelihood because we can't multiply it by an arbitrary positive constant. There is this value 1, because as soon as I know the relative belief ratio, which side of 1 it's on, I know whether I have evidence in favor or evidence against. And I can't divide by the maximum either, because that would destroy that interpretation. And also, if I'm interested in a marginal parameter, some function of theta, there's a problem for the naming construction. I don't think there's a solution to that problem so far. And that's almost 100 years ago, right? How do I deal with nuisance parameters? There are ways that people have proposed in the literature, typically profile likelihoods, but there's a significant problem with profile likelihoods. Sometimes they give very poor estimates, and also they're not likelihoods generally. Okay, but we have an easy solution in the Bayesian context, right? We just integrate out nuisance parameters. And that leads us to a new inference space, Bayesian inference space. We get the prior distribution on the side, because we just integrated out the nuisance parameters, and we get a new statistical model the statistical model, each density in it is given by just averaging the densities in the original model with respect to the conditional distribution of the nuisance parameters given psi. Okay, so we have a new inference space, Bayesian inference space, a new model, new prior, and X. But everything I say about theta is immediately applicable to this new inference space. And again, I get the relative belief ratio is just the ratio of the posterior density of psi to the prior density, which is given by this formula here. Now the density is this m rather than the p. And that is a likelihood function again. So a likelihood function with respect to this model and given this data. It's definitely a likelihood. A likelihood, what is it? Well, it's something that's proportional to the probability of the observed data as a function of the parameter, right? And that's exactly what I have here, okay? So I can just go right ahead and apply everything I just said about measuring evidence. I've got the relative belief ratio for psi naught to assess the hypothesis that psi naught is a true value, and I get the strength in the same way, right? And the relative belief ratio totally orders them, so I get the estimate by taking the maximum of the relative belief ratio for psi, which of course is just the supremum of that likelihood function, which is the MLE with respect to that likelihood function. So the MLE, even though some people think it's not a Bayesian estimator, is a Bayesian estimator. It's the value of the parameter of interest, here psi, that has the most evidence in its favor, which is an alternative of justification for maximum likelihood estimator. And a plausible region is given by obvious form, and you'll notice it's given the relative belief ratio greater than 1 is equivalent to set of psi, the relative belief ratio is greater than 1, is equivalent to the likelihood being, as a function of psi, being bigger than this constant here, m of x, right? The prior density of the data evaluated at the observed data. So the plausible region is always a likelihood region, always. Okay. And you can also get relative belief credible regions by taking the relative belief ratio bigger than some constant. There's only, and that's also a likelihood region, by the way, but there's one constraint on it. We don't want to report values as possible values for psi if there's evidence against them. So we must have that the posterior content, gamma, of this credible region is at least equal to the posterior content of the plausible region. Then the credible region sits inside the plausible region, and I know every value that I report has evidence in its favor. If I let the posterior content be bigger than the posterior content of the plausible region, then I'm going to be reporting some values that have evidence against them, which doesn't seem to make sense. So I apply that to that previous problem. And indeed, here's my plausible regions. Okay, so forget all the calculations here, although I will say something about a little bit about that table in a minute. Here's my plausible regions, and here's the posterior content of them. And you'll notice all of these are likelihood regions, right? They're comprised of the maximum likelihood region in each case, right? Okay, so now, one thing to notice here is that sometimes the relative belief ratio is equal to 1 in this little simple example. And what does that mean? Well, that means I have no evidence either way. And why is that? That it turns out because in the models that I wrote down earlier with a uniform prior, I didn't say that theta and the data are completely statistically independent, right? So I can learn nothing, when I observe 1, I can learn nothing about whether theta 3 is true or not. So another interesting thing to note here is that the plausible region only depends on the principle of evidence. And what I mean by that, if I use another valid measure of evidence, and by a valid measure of evidence, I mean something that agrees with the principle of evidence. There's a cutoff, so I know that it's bigger than the cutoff, I get evidence in favor. If it's less than, I get evidence against. And so I get the following theorem. And so it doesn't matter. I could use a Bayes factor. There are other measures of evidence. The plausible region is independent of any valid measure of evidence. And so I get the following theorem, which I call a theorem. It has trivial proof, so it's not hard to prove, but I think its consequences are quite profound. Namely, if I accept the inference base, okay, that means I integrated out the nuisance parameters, or this is the inference base for the full theta. Okay, I don't need to do any integration with integrating over nuisance parameters when theta, when I have the full model, right? I don't have psi is equal to theta, in other words, and I accept the principle of evidence. That implies that the estimate with the most evidence in its favor is the MLE. And if I'm going to quote a region for assessing the accuracy of the estimate, it must be a likelihood region. And the reason for that is if I don't record a likelihood region, then I know there is no, even if I don't like priors, there's no prior out there that would give me that region back as being the region where there's evidence in favor of those values being true. And in fact, I may well be reporting, and we'll see later, it happens, I may well be reporting a region for which there's evidence. Some values have evidence against them being true. And the FCCI, we've already seen that construction does not satisfy third one. So that's a second complaint. It doesn't, the construction, the name on construction does not give me intervals that satisfy the likelihood ordering. Okay, now I'm going to skip over this because I see my time is running a bit short here. So these ingredients that I propose, the model and the prior, these are subjective. They're both choices made by an analyst. We know how to check models. Perhaps not so well known is that we can also check priors. And I had a number of papers on that. There's a way to check the priors. So we'll just skip over that because it's not exactly germane to what I'm going to talk about here. But these biases are. I mean, the natural question to ask about Bayesian inferences is about the reliability. And this is where I think frequentism really excels, because it does talk about the reliability of inferences. We conceive of this repeated sampling idea. We perform the experiment over and over again, and we see how our inferences behave with respect to errors, right? So let's consider the hypothesis where I want a problem where I want to assess the hypothesis that the true value of psi is psi naught. I compute an error probability here. This is a probability, it's a frequentist probability with respect to the model that I get by, averaging out the nuisance parameters. What's the probability I don't get evidence in favor of the hypothesis when the hypothesis is true? We want that probability to be small. It's a probability of making an error. We can also talk about, I call that bias against. If that probability is big, you got evidence with very high probability that that's what you were going to get before you even collected the data. So that bias is certainly relevant, that error probability. Also, we get, this is of course like size in Neyman-Pearson type or typical frequentist testing, right? Also, we get the bias in favor, which is basically, I won't go into the details here, but it's the probability of covering values that are getting evidence in favor of values that are false. Okay, so psi naught is false and it's meaningfully false. So the difference between psi and psi naught is bigger than some delta that I've determined is what measures whether two values are different, meaningfully different or not in this application. And so if this probability is big, if I get evidence in favor of the null hypothesis that psi naught is true, well, that's not meaningful, right? Because if that probability is big, I knew even if it's meaningfully false, very likely I'm going to get evidence in favor. So I want both these biases to be small. And that's for a hypothesis assessment. For estimation, you just take the average of those, average over psi, right? Those two errors. Now, there's an interesting thing that happens here. The average of this probability, the probability that the relative belief ratio is less than or equal to 1 is the same as the probability that psi, when it's true, is not in the plausible region, which I can write as 1 minus the probabilities that it's in the plausible region. So these equalities hold. And what is it? This is the prior probability that the plausible region doesn't cover the true value. And in virtually every application that I've looked at, you can find, if you look at this thing I have inside here, this probability, as a function of psi, there's a value psi star that maximizes it. And so what do I know? I know that 1 minus that maximum is a lower bound on the coverage probability for the plausible region. So this lower bound serves as a true frequentist coverage probability for the plausible region with respect to this model, right? Now, if I'm not averaging over nuisance parameters, this is the model for the original model, but I have no problem averaging over. Some people complain about averaging over nuisance parameters, but my response to them is, okay, tell me what to do. The most logical method that I've seen is averaging over nuisance parameters. And similarly for bias and favor. So this is the prior probability of a meaningfully false value not being in the implausible region. The implausible region is just a set of all values that have evidence against them. If something is false, we want it to be in the implausible region. Now, the nice thing is all these biases converge to zero with increasing sample size. So before you conduct your experiment or your data analysis, your collection of data, you can calculate these things and see, okay, I want these to be small. How much data do I have to collect to make these biases small? So in the end, I have inferences that I trust. Now back to the Poisson one, right? So the physics problem. So I have a sample from a Poisson, lambda plus b, and I'm going to transpose that b is known here. Right? And physicists do experiments, and so they have some idea about the noise background in their experiments, and so they have a pretty good idea of what B is. And I'm going to take a gamma prior. Now, anytime I talk about Bayesian methodology, I always think one should talk about how I would elicit such a prior, right? So here, what I say is, I'm going to specify an interval such that I know that the true value of lambda is in that interval with virtual certainty, say probability 0.95, or it could be 0.99 or even bigger. And I'll specify the mode. Well, the mode for a gamma is equal to this formula here. And so for these two hyperparameters, I know tau1 is equal to 1 plus the mode times tau2. And tau2 is found such that this interval for the gamma distribution contains that gamma of the probability. Well, gamma here was 0.95. I guess that's not the coverage probability. I'm using gamma too many times. Make that 0.95, right? And so that determines my prior gamma rate lambda tau1 tau2. Now, as an experiment, what we did is my co-author and I, we generated data from a Poisson 6, and that seems small, but this is actually does correspond to something that happens in physics type experiments, right? Where they get very small counts. And I'm supposing the true value of lambda is 5 and that b is 1. And basically what we wanted to do, we wanted to test a hypothesis that there are no new particles. So we took an exponential, which has its mode at 0, right? So I know that tau1 is equal to 1. I specified the interval to be 0 to 10, and that led to a gamma, that elicitation procedure led to a gamma 1, 0.30 prior. Now, okay, so here's the bias calculations. Here I have frequentist confidences. So at 0.70, and by the way, these are confidences with respect, true frequentist confidences with respect to the Poisson model, right? These are the probabilities. These are the probabilities of true value. And you can see that it gets up pretty quickly, right? Even at 10 values, I'm at 90%. And I got to go basically to 25 values to get a 95% coverage probability. Now, these are the Bayesian confidences. This is where I average over all the possible values of psi. And they're generally a little bit bigger, right? But if you're dead set on having frequentist coverages, these are here. And also I looked at the biases against for testing the hypothesis that lambda is equal to 0. No new particles have been discovered. And at 10 values, I've got the 5% level for the size, if you like. And these are the biases in favor. Now, bias in favor is harder, right? So you have to specify delta. So I've given 3 tables here. Delta, that's a meaningful difference. Delta equals 1, delta equals to 2. And you can see I have to get up, well, even at 10, I've got 16%, right, probability of covering a false value, right? As I make delta bigger, the probabilities go down. As I make n bigger, the probabilities go down as well. So these are for the hypothesis testing problems like power there. Okay, that's what this column is, just power, if you like it, with delta equal to 1. And this is power at delta equal to 2, and this is the probabilities of covering false values. Now here, okay, so this is an actual data analysis, and I apologize for the quality of these pictures because they came off the paper and somehow they don't look good on the screen. So we generated a sample of size 10, produced 57 events, and so the MLE here is 4.70. That's easy to figure out. I checked for prior data conflict. There's no prior data conflict, as you would expect, right? And I plotted here the prior posterior. So on this plot, the left-hand plot, I have the prior, which is the green. The posterior is the blue. And over here under red is the relative belief ratio. Now remember, the relative belief ratio is proportional to the likelihood, right? So here's I do the cutoff at 1 because the values between the two blue lines down here, though that's the plausible interval, right? And the values between the two orange lines, those are the values I would get from the Feldman-Cousins interval, which is the commonly used interval in physics, right? Particle physics. Now notice here, it's definitely the Feldman-Cousins is not a likelihood interval. In fact, what's wrong with that, if I look at a value out here, well, it has it's a bigger likelihood than a value over here, right? But this value is not in the Feldman-Cousins confidence interval. I think that's illogical. Okay, so that's perhaps my major complaint with the Feldman-Cousins. These intervals are not likelihood intervals as in this context. And if I test, well, here, I'll go quickly through this. There's strong evidence against the null hypothesis, as you would expect. The plausible region is this plausible interval, is this interval, and its posterior content is 0.94, right? And this is based on a sample of size 10. So we know from a sample of size 10, the confidence is 90%. So there's no reason for the posterior probability content and the coverage probabilities to be the same. The posterior content here is bigger, 0.95, and the confidence is basically 90%. And the bias in favor, it's big. It's 0.221, right? I gotta say, a sample size 10 could be viewed as being relatively small, I guess, right? If I want that to be smaller, I have to take a bigger sample size. And my conclusion here is that the FCCI violates it. Now, we did a simulation. That's one set of data. So we did a simulation, generated lambda from our prior, and we generated the data, right? And then we worked out, well, how often does the Feldman-Cousins interval violate evidence, right? In other words, it has values in it that have evidence against them. And these are the probabilities of that occurring for different sample sizes. You can see even for 10, the probability of the Feldman-Cousins, even though it didn't in the previous numerical example, it did contain values that had evidence against them, the probability is about 30%, even with a sample of size 10. Now they do go down as sample sizes increase, which is good. But look over here, these are the probabilities that it violates, the Feldman-Cousins violates the likelihood of ordering. And these are always quite large, even at sample size 100. And if you those probabilities, and one other table here, I want to calculate what's the probability in my simulation that the Feldman-Cousins covers false values, the meaningfully false values. And these probabilities are very high, at least compared to the probabilities for the plausible interval, right? So you can do the same thing in B's unknown, except now you just integrate out. You put a prior on B, which will be a gamma again, and then integrate it out. And you get, if you look in the paper, we've done that there, and you get values very similar. There's nothing really different about the analysis. So just finish up. Principle of evidence provides a natural characterization of evidence when all the probabilities are known. This is directly applicable in the proper Bayesian. Even if there isn't a prior, I contend you want the intervals that you report, whether they're confidence intervals or they're credible regions, you want them to obey the likelihood ordering. Because if they don't, that means there's no prior for which that prior would say the interval you're reporting contains values that have evidence in their favor, right? Now, the Neyman, Feldman, Cousins, that violates that. So I think the I'm trying to advocate to the physicists that they use these plausible intervals instead. And the relative belief combines both Bayesian inference and frequentism. There's no conflict between the two. I just think, generally speaking, the relative belief inferences have better properties from a logical, soundly based on logic, and they have better properties than Bayesian or frequentist procedures generally. Thank you very much. And I'm sorry if I went a little bit too long.
Hello. So thank you, Professor Evans. Any questions or clarifications required?
Sir, can I?
Yes, please.
Yep.
Sir, two observations that I want to make. Sir, the very first one is that for testing a particular parametric value, do we have any estimate for the evidence of the nuisance parameter? That is, estimate of the strength of nuisance parameter. This is one. And my second doubt is, instead of taking ratio for relative belief, is there a way of considering difference instead of ratio? Do you have any such theory?
Yes. Yes. First of all, you could estimate the nuisance parameters, of course, using relative belief. You could do that. I don't think I would advocate doing that, but one could do that. And for the second question, yes, you could use the difference. But your plausible region is going to be exactly the same. Now, the relative belief ratio itself, because of its links with the likelihood function, has a lot of good properties. For example, all the inferences, when you use the relative belief ratio, the estimate, etc., they're invariant under reparameterizations, just like likelihood. Now, if I use the difference, they're not. Okay, so my estimator will not be, or the credible regions I report, etc., will not be invariant under reparameterization. So yes, you could be. You could use an alternative. You could use a difference. You could use base factor, properly defined. That's another issue. But you could also use the base factor. But there are many reasons why the relative belief ratio, I think, is a better way to go there. In fact, much of all those calculations that I did about bias, etc., they don't depend on what measure of evidence that you use. Really, only the strength of evidence that I computed for the hypothesis testing, that is the one that, and the posterior probabilities, right? Those depend on which evidence, a measure of evidence that I use, but not much else.
Thank you. Thank you very much for your clarification, Professor.
Thank you.
Any more questions? Hello, any more questions or clarifications required? It seems no more clarifications or questions are there. So on behalf of the conference committee, let me thank you, Professor Evans, for the nice presentation. And also usually we don't see applications in physics, that too in particle physics from statistical analysis. So it has been a very quite interesting, though that physics aspect I couldn't follow that much. But still, it was quite interesting, and also to note that we have applications to so many relevant fields. Once again, thank you, Professor Evans, for your time and the nice presentation. Thank you very much.
Thank you very much. I enjoyed it.
Thank you, Professor Evans, for your wonderful talk. Thank you.
Thank you. Bye-bye.
So I think we have some time for this before concluding this session.
Okay.
So is Professor Manoj Kumar Tiwari is available there? Professor Tiwari, are you there?
Yeah, I'm available. I'm available.
Oh, okay, sir. You are most welcome to this session.
Thank you very much.
Session. So your presentation will be on. Adina, please give an introduction to Professor Manoj Kumar Tiwari, so that we can start straight away without losing time.
Our next speaker is Dr. Manoj Kumar Tiwari from Sultan Qaboos University. He brings significant international research and academic experience in advanced regression techniques and applied statistics. We look forward to an insightful presentation and fruitful discussion that will enhance our understanding of recent advances in statistical theory and its applications. With great pleasure, I invite Dr. Manoj Kumar Tiwari to this session.
Professor
Thank you very
Tiwari,
much. Thank you very much for.
invited to this session. So please take about 20 minutes, okay? I hope we can
Okay, it's a 20-minute session.
20 minutes. 20 minutes.
Okay.
Okay.
All right.
Okay.
Okay. So let me make it big. So here in this one, yeah. So in this one, I'm going to give a talk on a novel two-parameter estimation for the Kumaraswamy regression model and its application. So basically, in this talk, I mean, I'll be talking about the introduction of a regression model for the double-bounded variable constraint within the interval of 0 to 1. For utilizing the Kumaraswamy distribution. So the model resembles almost like a generalized linear model, where the median of the response is represented by a regression framework using the logic link function. We will employ the maximum likelihood approach to estimate the regression coefficient. And later on, we will work on a novel bias estimator referred to as the two-parameter estimator for the case of a Kumaraswamy regression model to mitigate the problem related which arising from the multicollinearity. So this will be the all thing, and later on we will analyze about the properties of a proposed maximum likelihood technique, presenting a closed form representing the case for a likelihood technique and expression for using a score vector, which will be considered in the form of Fisher information matrices. So, and additionally, we will work on the efficacy of the proposed estimator in assessed comparison to the maximum likelihood estimator and Liu estimator using the mean square and the mean square error criteria. And later on, it will be justified using the Monte Carlo simulation in order to compare the result over there. So overall, if you move ahead, so we can talk about the case of a regression analysis. So basically, if we talk about regression analysis, is used as a statistical technique for estimating the relationship between the one or more independent variable, and where it will be a response variable, which will be also mentioned as a dependent variable. Further, we take an assumption of a linear regression model in the independence variable when they are uncorrelated. Under this situation, when the problem of the multicollinearity arises, when this assumption is violated, then it goes with the case of a multicollinearity. So, or generally long back, like they used to work on the bounded data set in the case of a beta distribution, which was also they are called the double bounded distribution for response variable, or using the interval 0 to 1. And Kumaraswamy in 1980 defined an alternative distribution for the beta distribution, which came in the form of a Kumaraswamy distribution. Further, some work was done by Frisch in order to study the property of a multicollinearity under such situation in 1934. Then later on, a classical paper came up from the Hull and Kennard in 1970 to work on this, to deal with the problem of the multicollinearity. And then later in 1993, Kazian also produced a result which came in the form of a Liu estimator. So combining the idea of Stein and Ridge, so in order to overcome the problem of the Ridge estimator arising from multicollinearity. Later, Ferrari and Neto also proposed regression model for the case of a beta distribution for dependent variable. And similarly, Jones and other also work on that one. So latest in the 22 Abonagel, he developed a new two-parameter estimator for the case of a beta regression model to overcome with the problem of the multicollinearity. So here we consider the case of a Kumaraswamy regression model for the dependent variable, and we did the multiple calculation for the case of a beta distribution. And the probability density function of a Kumaraswamy distribution is given with the interval of 0 to 1, and then the cumulative distribution function came up. And further, in the case of a Kumaraswamy regression model, we consider yi be sample of n independent random variable following the k, mi, and phi. This is probably where mi here is the median and phi the nuisance parameter in this case. So now, after modifying, it came the Kumaraswamy regression model came in this form, which is GMI for the xi transpose beta for I equal to n. And this is the link function, because we'll be using the link function in order to convert with the case of a two-parameter estimator to work on. So further, then we go with a random component that will identify the probability distribution of a random variable with the systematic component specified in the case of a linear function for explanatory variable, and that will be used as the predictor one. So the link function here, it will be you will be using the link function, which will log of psi I divided by 1 minus psi I, where psi I is the linking parameter. So we'll be using this in order to convert that into case of a two-parameter estimator to work on our problem. So further, when the maximum likelihood estimator was coming up with the case of a Kumaraswamy regression model. So Kumaraswamy regression model does not have a closed form for this equation. So we applied, as I mentioned earlier, that we'll be applying the Fisher scoring technique in order to obtain this estimator. So from the Fisher scoring algorithm, this is mentioned the Fisher score, where theta is the parameter and theta to the power p is the estimate of the parameter, and we'll go for the p iteration where p is greater equal to 1. Then so score function, in this case, it will be the gradient partial derivative of the log likelihood, which will be mentioned over here, the Fisher information matrix. It will be represented by I theta. It will be using in this equation number 5 to work in the form over here. And further, we'll move forward. So now we'll consider theta, which will be the vector of the parameter over here. And then we take a log likelihood function for the Kumaraswamy regression model for this case, and it will come up. So after performing, going for the pth iteration, we'll get the maximum likelihood estimator for the beta. It will be obtained over here in the form of beta hat KML, Kumaraswamy U, with phi, and this one, where G, where the G mentioned over here, it will this form, and W star will be the diagonal, and WI star, WI square. Here, these are WI star hat and G hat, which we have explained in this one, is a form by replacing the parameter beta at the pth iteration, which we consider p greater than equal to 1. Further, we moved toward the working on the case of a mean square error matrix criteria. So here in the mean square matrix estimator,